This is a diagram of a typical electric circuit. This circuit is powered by a battery. The battery we see at the bottom. We've seen this kind of diagram before. It's showing us the relationship between electron drift and electric current. The electron drift is indicated by a yellow arrow that's pointing counterclockwise around the entire loop of wire. It goes from the negative terminal of the battery to the positive terminal of the battery. And this makes sense because the negative terminal of the battery is going to repel electrons, push them around the circuit, and then the positive terminal of the battery is going to attract the electrons. Remember, though, that the direction of electron drift is opposite the direction of current because current is defined as the direction of positive charge and electrons are negatively charged. So if the negatively charged electrons are moving counterclockwise around this loop of wire, then the current, the positive charge, is actually moving clockwise around the circuit. So what would happen if instead of just having a battery connected like it is permanently to opposite ends of the wire, what would happen if you reversed the battery, just flipped it around? What would happen to the electron drift and the electric current? Well, if you flip it around, then the electrons would be repelled they would still be repelled by the negative end of the battery and attracted to the positive end. So the direction of electron drift would reverse. The electrons would switch to the electrons would switch to a clockwise rotation, and that would mean that the current would switch to a counterclockwise rotation. So what if you could instantaneously and repeatedly flip the terminals of a battery, like faster than even if you just rotated the battery, like put it on a spinner and spun it around, but you could actually flip it instantly back and forth? Well, what would happen to the current? We would have the electron drift going back and forth, and so the current itself would also go back and forth. It would, instead of flowing from one end of the battery to the other end of the battery consistently, it would flow back and forth through the wire. This is called alternating current because the direction of the current moves first from left to right, and then it moves from right to left because the electrons are moving back and forth rather than through the wire. They don't move all the way through the wire even. In fact, it's a bit of an overstatement. So the electrons, they kind of wiggle back and forth through the wire. They move a very small distance. But moving electrons, when electrons are all moving in the same direction, or mostly many of them are moving in the same direction, they create an electric field around the wire and a magnetic field around the wire, and the field is actually what carries the current. So electrons don't have to move far to create a field, and so in an alternating current circuit, where the positive and negative poles of the power source are rapidly switching back and forth, the electrons just wiggle back and forth, and thus they create a current through the wire. Many electrical components, like light bulbs, certain types of motors, and other things, household appliances, function in the same way, regardless of the direction of the current. As long as there's a current moving through a circuit, you get some kind of reaction out of the appliance. So alternating current, the device has to be designed for alternating current or direct current, but devices that are designed for alternating current work with this little wiggling of electrons rather than a continual flow of electrons. The standard frequency of alternating current in North America is 60 hertz. That means you have 60 back and forth cycles per second. So the direction of the current flips back and forth 60 times every second. And different different countries, different parts of the world will have different standard frequencies, but all of our appliances are designed to handle that 60 hertz frequency. We use high voltage power lines like this to carry current across very large distances. We have to be so these power lines. We don't want to have power plants all over the place. Okay, we don't want power plants all over the city. In fact, when soon after Thomas Edison invented or discovered invented electricity, means to um, generate electricity, it became apparent to people to industrial people that they could really benefit by supplying electricity to people's houses. I mean, remember before that, nobody had electricity in their houses, and now we have it all over the place. Imagine if you had to have a house with no electricity, it would be really unusual. Well, in the early days of electricity, there was a battle. Well, not a physical battle, but a very heated argument about whether power grids of the public, whether the public power grids would use alternating current, AC, or direct current like a battery. Thomas Edison actually wanted to design power grids that used DC, direct current. And that would have required essentially battery stations all over the city because direct current can't travel really far. It becomes less efficient the farther it travels because remember, it's continually pushing electrons in one direction through the wire. And as it pushes electrons through the wire, it gets weaker over a distance. Well, with alternating current, AC, the electrons are just wiggling back and forth. And so they never travel a great distance. And so we can have these long power lines. And um, this is a mechanism that was supported by Nikola Tesla. So Nikola Tesla developed the technology to provide alternating current. So there was this big back and forth argument and competition between Thomas Edison and Nikola Tesla. And eventually, Tesla's ideas won out. So we have these high voltage power lines. Sometimes they're suspended in the air, like we see in this image, especially in remote areas. We'll have these aerial lines because they're easier to access. But in some residential areas, some highly populated areas, sometimes they bury these lines underground. So sometimes you can't even see them. But they're there and they carry electricity from one property to the next. Now, if you have this high voltage AC electricity, you have to reduce it in order to be used uh, by consumers. And the way that we reduce the current is with a device called a transformer. The transformer changes the voltage and the current of the wire. And this is another reason why we use AC, not only because it can be carried over a long distance better than DC, but because it can be run through a transformer much more easily, much more effectively, to reduce the voltage. So we can carry it from one place to another at a very high voltage. And then once it gets to where we want to use it, it gets stepped down to a lower voltage. You have transformers around your neighborhood. You might not notice them, but they're like the utility boxes, or they're the electric structures that you see just around neighborhoods. And sometimes a transformer will blow out if it gets hit by a lightning or something like that, and then the neighborhood will lose its electricity for a while. The electric company will come out and fix it, and then we've got electricity again. Not a huge deal, but the ability to transform high voltage to low voltage electricity makes AC very valuable. And the way that a transformer works, essentially, is that the electric wires, the high voltage electric wires, they electrify a coil of wires, and then the coil magnetizes an iron core. So there's a magnet that's formed by that coil, and then the magnet in turn uh, induces an electric current in a second coil, a secondary coil. The the reason that the voltage decreases is that the primary coil and the secondary coil are different. So the primary coil has more turns in it, more loops in it. It magnetizes the magnet, and then the magnet uh, induces current in a coil with fewer loops in it. So it is a lower voltage current that then can be carried to homes and businesses.